Okay, so the next speaker is Hyunsuk Kim from Michigan, and he'll talk about some analytic and topological aspects of Hodge modules.
Thanks for the introduction and the opportunity to talk. So I believe that the how can I say? I think that the power of Hodge theory is that it really provides a bridge between three different a priori unrelated objects, like the topology of algebraic varieties and the complex analysis on them, and the coherent theory of I mean, the algebraic theory. So you can already see this from the classical uh, Hodge theory of smooth projective varieties. So the first one is the singular cohomology of X, which is like a topological object. And it is known that the representatives over here, the cohomology classes on mid are representative by certain harmonic forms, which comes from analysis. And these parts have some algebraic meaning, like some sheaf cohomology of coherent sheaves. So, and there's like a strong functorial package of Hodge theory that allows to do Hodge theory on arbitrary varieties, and these are called mixed Hodge modules. And actually, already from the definition of Hodge modules, these three, how can I say, these three pillars already persist. So a Hodge module is a filtered D module, first of all. So this is like a coherent or a quasi-coherent data with an underlying perverse sheaf, which is a topological data that talks well between the D module and the perverse sheaf under the Riemann-Hilbert correspondence. And there is also an analytic input, which is the existence of a polarization. Uh, so for example, this if your variety is smooth, then your OX is a D module whose underlying perverse sheaf is the constant sheaf shifted by n. And this is a Hodge module, and there is also polarization on OX given in the obvious way. So over here, I'm kind of using the convention of complex Hodge modules, but uh, the data of the polarization is over there. And somehow, though, the most of the heavy theory of Hodge modules are really concentrated on filtered T modules, so the coherent side. But actually, most of my research is somehow exploiting the relation between the topological uh, properties or the analytic properties of Hodge modules with the uh, coherent world. So yeah, this talk will going to be some series of small things that of what we can do uh, using these objects. So the first thing is the Saito's vanishing theorem. So when Saito developed this theory of Hodge modules, he proved a vanishing theorem of coherent sheaves. So if you have any mixed Hodge module, then if you take the graded de Rham complex, which is some object in the derived category of coherent sheaves, and you twist it by an ample line bundle, then the cohomology of these one vanishes. And this is truly a vast generalization of this classical Kodaira Akizuki Nakano vanishing, since when you put your if when your Hodge module is a trivial Hodge module on X on a smooth projective variety, then it really recovers the classical statement. And Saito's original proof used some topological input, which is called the Artin-Grothendieck vanishing of, in the case of perverse sheaves. And I revisited the Saito's vanishing theorem and gave a proof using L2 methods, which essentially goes back to the idea of Kodaira. So let's see how Kodaira proved this theorem. So the essential idea of Kodaira is that the positivity property of the curvature of a line bundle somehow enables us to solve the D-bar equation, which actually implies some vanishing of cohomology. And actually using some curvature formula for Hodge bundles and a precise estimate or a precise description of how Hodge structures degenerate, I was able to prove these Saito's vanishing almost in the same way as Kodaira proved his vanishing theorem. So this is some interplay between analysis and how to say coherent cohomology for Hodge modules. And the next one is some interplay between some topological properties and the coherent world. So here I think of a toric variety. So when you have a toric variety, this intersection complex, I see this is a very well understood object in the level of constructible complexes. And the question is, if you enhance this structure as a Hodge module, what else can we get? So for example, if you take the graded drum complex again, so this is some object in the derived category of coherent sheaf, which can only be seen after enhancing this object to a Hodge module, enhancing this intersection complex to a Hodge module. So using some toric geometry, we can somehow encode this data of this graded drum complex by some generating series. So there is this generating series dr. So what you can do is you have the graded drum complex, and you can take the cohomology. So this is a genuine coherent sheaf. And by using this torus action, you can encode the, how can I say, the degree U part with respect to the torus action. So this is some generating series encoding the graded drum complex of the intersection cohomology. And this H tilde is really some topological data. So we're encoding the stocks of the intersection cohomology complex. So H tilde is something topological, and this drum is something coherent that you can see after enhancing this intersection complex to a Hodge module. And in a project with Sridhar Venkatesh, we showed that this generating series dr is actually somewhat completely determined by the data of the underlying perverse sheaf in some non-obvious manner, but it's completely determined. And building up on this work, we are able to answer some questions on the local cohomological dimension of toric singularities. So for a singular variety, which we can embed this singular variety into a smooth one, and we ask where the local cohomology lives in. So it's a classical fact that the local cohomology starts at the codimension, and the other end of the cohomological amplitude, so the maximum of this Q that the local cohomology does not vanish, is by definition the local cohomological dimension. And this is somehow the subtle invariant coming from commutative algebra. And actually, the difference between these two, so the LCD minus the codimension, we call this the local cohomological defect following the terminology of Popeye and Shen. And this turns out to not depend on your particular choice of embedding. So this can be understood as some invariance of singularity arising from commutative algebra. And it's kind of easy to see that if your variety is LCI, so if your variety is cut out by the correct number of equations, then this quantity is zero. So in some sense, this quantity is measuring how far your variety is from being LCI. And in general, toric varieties are very far from being local complete intersection. And using some Hodge module techniques, we are able to actually compute this local cohomological defect just in terms of linear algebra of finite dimensional vector spaces. So what's important over here, the key ingredient that we use are actually the Hodge module structure on local cohomology. So by Saito's theory, these objects, which you can easily see that this is a D module, actually carries an extra structure of a Hodge module. So you have a natural filtration on them, and using this filtration, you can compute this quantity local cohomological defect. Yeah. And what we use to compute these quantity is some very precise control on the Grothendieck dual of what is called the Dubois complex, and also the underlying by studying the underlying topological structure of the constant sheaf on your singular varieties. And by doing that, we actually have some byproducts. So there is like a very precise combinatorial description for these X sheaf of this Dubois complex. And we have some non-trivial vanishing results coming from Hodge theory, the theory of Hodge modules. And actually, this implies a purely combinatorial result on rational polyhedrocones. So this is one thing that we get. And also, we can not only detect the somehow a coarse invariant, the local cohomological defect, but in some case, we can carry out the precise structure of this trivial Hodge module, which is really trivial if X is smooth, but in general, it's very hard. I mean, this trivial Hodge module is a very hard object to fully understand. But in some cases, in some toric cases, we are able to do it. And by understanding this structure of this trivial Hodge module, we have a better understanding on the Hodge structure of singular cohomology of toric varieties. So here is one example. So this hypersurface is defined by a binomial equation. So this is a toric hypersurface, and it's moreover some kind of singular cubic fourfold. So the smooth object, the Hodge diamond, looks like this. So this is a hypersurface. So the only interesting cohomology is the middle cohomology over here. And the middle cohomology somehow looks like a K3 Hodge structure. And if you compute a singular cohomology of S, then we have this behavior. And if you see the middle cohomology, what we have is dimension 1 on weight 2 and dimension 4 on weight 4, and both are of Hodge type. So, and we can also see that any degeneration from a smooth cubic fourfold to this particular toric hypersurface is somehow maximally unipotent. And actually, this toric hypersurface is one of the most degenerate loci among all the GIT polystable cubic fourfolds that Radu Laza classified. And Radu Laza also studied how the period map extends from the GIT moduli to the Bailey-Borel compactification of the Hodge structure of this type. And this particular toric hypersurface has to map to the deepest strata of the Bailey-Borel compactification of the boundary. So it is, in some sense, some maximally unipotent monodromy degeneration. And using some toric methods, we can also compute the binomial hypersurface given by this equation, which behaves exactly the same as this toric cubic fourfold case. Yeah. And actually it turns out that we can do a little bit more. So instead of just thinking of two terms, now we're thinking of L terms. And if L is equal to 1, this is really the toric boundary Calabi-Yau. So this is the maximal unipotent monodromy SLC degeneration of Calabi-Yau hypersurface that mirror symmetry people like. And for L equals 2, this is a toric variety, and these hypersurfaces has 1 Dubois singularities, and Hodge theoretically, it behaves exactly the same as this maximally unipotent monodromy Calabi-Yau degeneration. So, for example, if you have this if you see this middle cohomology, it really Hodge theoretically is maximally unipotent. And what I can show is that for higher L's, this kind of phenomena persists. So when L is equal to 3, so this is an example of a cubic sevenfold, and now this turns out to have better singularities, so it has 2 Dubois singularities. And if you consider a smooth cubic sevenfold, the Hodge structure is somehow like a Calabi-Yau 3 Hodge structure. So there's 1 on the end and 2 more zeros. So this is a Hodge structure of weight 7, but it comes from some Tate twist of some Calabi-Yau 3 type Hodge structure. And if you compute a singular cohomology of this degenerate hypersurface, the Hodge diamond looks almost the same as before. So there are ones over here, and there's like a small branch coming from 9, where the numbers are fairly computable. So maybe why am I interested in this hypersurface? So there is I think it will be an upcoming work of Sung-Gi Park that who actually discovers a very tight relationship between this GIT moduli of, let's say, Fano hypersurfaces and this higher Dubois and higher rational singularities. And he has a notion of, how can I say it? Notion of sources in this setting, in this Fano hypersurface setting, which actually behaves exactly the same as the minimal log canonical center or the source in the classical Calabi-Yau setting. So the cohomology of the source, in some sense, how can I say, detects the transcendental lattice of the limiting mixed Hodge structure. And in this final case, the source is not something super geometric, but some part of some Hodge module living on the singular hypersurface. And in this case, the source is just a point. So, and this in particular implies that any one parameter smoothing of X is a maximally unipotent monodromy degeneration. And what I can do is I can also compute the singular cohomology of this hypersurface in general, and this really looks the same as the toric case. So you will have ones on the middle, and then there will be some branch that ramifies from a certain place, and you can compute the numbers fairly explicitly. You can also compute the intersection cohomology of this hypersurface in a pretty explicit manner. So all the intersection cohomology is of Hodge-Tate type, and we have a precise formula for the intersection Betti numbers for it. And also, so this is like a mildly singular Fano hypersurface. So I think it's natural to ask whether this hypersurface is K-stable, semi-stable, or polystable or not. And you can easily see that there's a huge automorphism group by swapping these variables. So this is some finite group. And also there's a torus action. And it turns out these are all of the automorphism groups of X. It's not so hard to see that these are all. And by using this action of this automorphism group, I also can prove that this hypersurface is K polystable. So in particular, uh, in the perspective of GIT, there are lots of intermediate strata um, between the smooth hypersurfaces and this particular one, and somehow the polystability of this final hypersurface also implies that the lots of intermediate, how can I say, intermediate singular final hypersurfaces are also K polystable or semi-stable. I think this is all.
Okay, thanks so much. Any questions? Okay, so if there are no questions, okay, let's thank Hyunsuk again and let's take a break.